The next topic is orthogonal matrices. These are a particular kind of matrix. They come up a lot in applications in lots of different areas. It might not be obvious at first why they're so important, but maybe just take my word for it for the moment. So let's give the definition. It's a very simple definition. Q is an n by n matrix. We say that Q is orthogonal if the following single condition holds. Take the matrix Q transpose and multiply it by itself, you're supposed to get the identity. That's it. That's the definition of an orthogonal matrix. What does that mean? What's this about? I don't understand. What's the point? Okay, let's see. Let's do an example. Let's take a 2 by 2 matrix. A, B, C, D. Then the condition is that the transpose A, B, C, D times the matrix itself, A, B, C, D, is supposed to equal 1, 0, 0, 1. So what does that say? That says A squared plus C squared equals 1. Well, that's encouraging. That's a circle or something. So what's the next condition? The next condition is that AB plus CD is equal to 0. And the next condition is the same. BA plus DC is equal to 0. And the last condition is that B squared plus D squared is equal to 1. So, what does that say? That says that if you look at the columns of this matrix, AC and BD, so you let V be the matrix, the vector AC, and you let W be the vector BD, then this condition is saying that the length of V is 1, or if you want, VV is equal to 1, where this is the usual, VW is the usual dot product. And this condition, AB plus CD is equal to 0, let's write that over here. That's the same thing as that saying that AC dot BD is equal to 0. In other words, VW is equal to 0, and this condition is the same, and then the last condition, BD, is about this vector. It says that WW is equal to 1. And I know you all look at this instantly and say, aha! What does that say? That says that these vectors VW are an orthonormal basis of R2, with the inner product being given by the dot product. Well, okay, that's a natural condition. It still may, might not be obvious why it's so important, but it does look like a reasonable thing. Okay, the first thing to do is to generalize that 2 by 2 result to Rn, and it's actually pretty easy. Here's the theorem. Suppose Q is an n by n matrix. Then Q is orthogonal. That's the definition I just gave. If and only if the columns of Q are an orthonormal basis. Of Rn, and of course with respect to the usual dot product. Okay, let's see, why is that true? It's actually pretty easy. Suppose Q was written like this. You write it as a bunch of column vectors v1 through vn. V1 through Vn. Then what's Q transpose Q is V1 transpose down to Vn transpose times V1 up to Vn, like this. And what happens when you multiply this matrix times this matrix? Well, the ijth entry is Vi transpose times Vj transpose. The ij entry of the result, Q transpose Q, is Vi transpose times Vj, which is just Vi dot Vj, which is, of course, Vi Vj. Okay? So that is, this matrix is V1, 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 V2, right. And when is this matrix the identity? Well, it's the identity means it's ones down the diagonal and zeros everywhere else. When is this the, well, this is the identity if all of the VIs are equal to 1 and all of the other VIVJs are equal to 0. So this is if and only if VIVJ is equal to 1 if I is equal to j and 0 else. And that's exactly the condition for these guys to be an orthonormal basis. Well, let's go back and look at the 2 by 2 case again. Suppose I have a 2 by 2 matrix which is orthogonal. So, among other things, this says that a squared plus c squared is equal to 1, and b squared plus d squared is equal to 1. And you all know, of course, that this is a circle, and necessarily a is of the form cosine theta, in which case c is sine theta for some angle theta. And similarly here, you're getting cosine phi and sine phi. And it turns out that you also have the condition that the dot product of these two vectors is 0. AB plus CD is equal to 0. This implies some relation between theta and phi. And I'm not going to work this out. It's really not that hard. But see page 236 in the book. What you conclude is the following fact. If Q is 2 by 2 orthogonal, then either Q is equal to cosine theta, sine theta, minus sine theta, cosine theta, or it's of the form cosine theta, sine theta, sine theta, minus cosine theta. And I'll point out that this is simply 1 minus 1 times the original matrix, cosine, sine, minus sine, cosine. This matrix is 1 minus 1 times that. And notice that the determinant here is cosine squared plus sine squared is equal to 1. And notice that the determinant here is equal to minus cosine squared minus sine squared, which is equal to minus 1. Okay, so there aren't an awful lot of orthogonal 2 by 2 matrices. If you just look at the determinant ones, guys, for example, the only ones are these ones given by an angle theta. And this is somehow rotations, this is somehow a circle. And I want to explain a little bit more what that really means. Okay, so I want to stare at this matrix a little bit and try and figure out how I can understand it. This is one of the types of orthogonal 2 by 2 matrices, cosine, sine, minus sine, cosine. And it's very helpful to think of this as being a map from R2 to R2, just the matrix gives such a map, which is to say cosine theta sine minus sine cosine. It takes the vector x y to, well, I should really write it as a column vector, but never mind. To x cosine theta plus y sine theta minus x sine theta plus y cosine theta. So, for example, let's take the vector 1, 0. Where does this go to under this map? So that's x is equal to 1 and y is equal to 0. I get cosine theta minus sine theta. That's interesting. Cosine theta minus sine of theta. And what does that mean? So it takes the vector, it's helpful to draw the circle. It takes the vector 1, 0 to cosine theta minus sine theta is, I'll draw it this way, this angle right here. It's rotation by the angle theta. So let's see, it takes 1, 0. The one thing to note is that this vector has length 1, and so does this vector. So how should I write that? Notice that over here, 1 plus 0 is equal to 1, and over here, cosine squared plus sine squared is equal to 1. So it's taking this point on the circle to another point on the circle, and the one it is rotation by theta. And if you plot a couple of other sample points, you'll see this is what is going on. This matrix is rotation by theta. And notice that it takes all the vectors of length 1, this matrix Q. If you apply it to a vector V, it doesn't change its length. That's one of the crucial properties of orthogonal matrices. A vector and Q times the vector have the same length. In this case, they both have length 1. And so if you think about it, what that means is in R2, for example, it takes the circle radius 1 to itself by some rotation. But the same thing holds for circles of any radius. So, right, it's taking all of these circles to themselves, and it's rotating the entire plane by some angle theta. And if you drew the same picture in R3, it's exactly the same idea, except that now it's taking the sphere to itself. It's some kind of rotation of the sphere. And the crucial point is this property. It doesn't change length. So it takes all the vectors of length 1 to themselves and all the vectors of length 2 to themselves and so on. So let me state that again. The fact is that if Q is orthogonal, then if you have any vector V, then the length of QV is equal to the length of V. All right, that's a very important property of orthogonal matrices. It doesn't change the length of vectors. So that says that if you're thinking of Q as a map from Rn to Rn, it takes the sphere of radius r to itself, the sphere of radius r. And so Q is, one way to say it is it's a generalized rotation. And I'll leave it to your imagination to think what this means in dimensions 4 and bigger, but it's some kind of operation which is like a rotation in R2. Okay, I'll do a couple of examples of orthogonal matrices in class. Let's look at another property of orthogonal matrices, and this is a very simple fact. If Q is orthogonal, then the determinant of Q is plus or minus 1. All right? And this fact is extremely easy. If Q is orthogonal, that says that Q transpose Q is the identity. And just take the determinant of both sides of this equation. You conclude that the determinant of Q transpose Q is the determinant of the identity. And that says, well, remember, the determinant of a product is the product of the determinants. And the determinant of the identity is 1. And the determinant of the transpose and the determinant of a matrix are the same. So this says that the determinant of Q times itself is equal to 1. So this is a number square is equal to 1. That says that the determinant is plus or minus 1. So this actually requires a little extra explanation right here. Q is a generalized rotation. This is, strictly speaking, only the case when the determinant is equal to 1. So these matrices, cosine theta, sine theta, minus sine theta, cosine theta, have determinant 1 in their rotations. But if you have something of determinant minus 1, that's something else. It's actually a reflection. And I'm not going to worry too much about that. So most of the time, we'll focus on the case when the determinant of Q is equal to 1. Okay, here's an amazing fact about orthogonal matrices. If Q1 and Q2 are orthogonal, then so is their products, Q1, Q2. Let's see what that means. So, for example, in R2, what that says is the following. If you rotate a circle by angle theta, and then rotate it again by another angle, well, theta 1, and then you rotate it by another angle, theta 2, then together, that's a rotation by theta 1 plus theta 2. So rotating a circle, if you do 2 rotations, you get another rotation. And let's see why this is true in general. It's actually very easy. If Q1 is orthogonal, and this is the kind of proof that you should be able to do yourself, at least maybe with a hint or two. You write down what this side means, and you write down what that side means, and you stare at it. So what does it mean for Q1 to be orthogonal? It says that Q1 transpose Q1 is equal to the identity. And similarly, Q2 is orthogonal, says that Q2 transpose Q2 is equal to the identity. And I'm hoping that this implies that Q1 times Q2 is orthogonal, which is to say this identity holds. Well, if something like this is going to hold, there's only one reason, which is you somehow work out this thing and it comes out. So the point is Q1, Q2 transpose, this is equal to Q2 transpose Q1 transpose Q1 Q2. And now if you just group these two guys together, these give the identity. And so what you're getting is Q2 transpose identity Q2, which is equal to Q2 transpose Q2, which again, because Q2 is orthogonal, you get the identity. So really it's elementary. Okay, let me do the first serious application of orthogonal matrices, and this is called the QR factorization. And it says the following. I'll just write it out. Suppose A is an invertible n by n matrix. Then I can find an orthogonal matrix Q and a matrix R, which is upper triangular, such that A is equal to Q times R. Any matrix can be factored into the product of an orthogonal matrix and an upper triangular matrix. And I'll say something about uniqueness in class. All right. So this is one of these things like the LDL decomposition, various kinds of decompositions. If you have a problem involving a matrix, it's sometimes useful to put it in one of these forms. And how do you know which form to put it in? Well, if you're looking for some property of the matrix having to do with an inner product, it suggests that it might be useful to put it into this decomposition because this orthogonal condition here has to do with the inner product.